Hello students, today we'll be starting a new topic, a linear programming problem. So let's see what do we know as linear programming. So let's start with the introduction. It is widely used uh, mathematical modeling technique to determine the optimal allocation of scarce resources among competing demands. Resources typically include the raw materials, manpower, machinery, time, money, and space. This technique is very powerful and found especially useful because of its application to many different types of real business problems in areas like finance, production, sales, distribution, marketing, and many more areas of management. So, the linear programming that we are talking about is a mathematical modeling technique used to determine a level of operational activity in order to achieve an objective. So, how do we formulate linear programming problem? What would be the major objective? Every industry, every business has an objective. So, whatever is your objective, either it would be your maximizing your profits or minimizing your cost or transportation cost. So, depending upon your objective, you would be having certain requirements, availability. So, we'll be converting them into inequalities and then we'll be writing them in the form of linear programming problem. So, this is a gist of what we'll be doing today in this lecture. A mathematical programming is used to find the best or the optimal solution to a problem that requires the decision or set of decisions about how best to use a set of limited resources to achieve a state of goal of objectives. So, what are the various steps that is involved in mathematical programming? First one, conversion of stated problem into a mathematical model that abstracts all the essential elements of the problem. Second, exploration of the different solutions. Third, find out the most possible or the optimal solution. So, in the linear programming or the mathematical programming, as you can see, the steps that are involved here is first of all, you have to understand the problem. You have to convert the problem into the objective function, the constraints, the inequalities. Then the second step would be we'll be finding out the different solutions of that particular problem. Then, out of those solutions, we'll be talking about the optimal solution. Optimal means that particular solution which will help in maximizing your objective function or minimizing. So, whenever we talk about objective function, is basically the objective of the business, and whatever is your objective, the optimal solution has to satisfy that. So the linear programming requires that all the mathematical functions in the model must be linear functions. That's why it is called a linear programming problem, because the degree has to be 1. So we'll be talking about it in the upcoming slides. Applications. As I told you, it has various applications in different industries, whether we are talking about the management, so different kinds of management, hospital, diet, manufacturing, finance, advertising, agriculture. These are the some of the applications of linear programming problem. So let us consider certain examples. A product mix problem. So a manufacturer has fixed amounts of different resources such as raw material, labor, and equipment. These resources can be combined to produce any one of the several different products. The quantity of the ith resource required to produce one unit of the jth product is known. The decision maker wishes to produce the combination of the products that will maximize the total income. So I'll be taking up this problem, the example in the upcoming slides, and I'll be showing you that if I'm manufacturer of bowls and mugs, and I have labor and I have the raw material, so how would be I combining them so that I can maximize my revenue? That means the total income. So this is a very common example where you in the linear programming problem. Next, we talk about the product scheduling problem. A manufacturer knows that he must supply a given number of items of a certain product each month for the next n months. They can be produced either in regular time, subject to a maximum each month, or in overtime. The cost of producing an item during the overtime is greater than during the regular time. A storage cost is associated with each item not sold at the end of the month. The problem is to determine the production schedule that minimizes the sum of the production and the storage costs. So whenever we are talking about the costs, it could be transportation, it could be the storage, the production cost, we always want to minimize it so that we can maximize our revenue, that means the profit. So another most important, the common ones I will say is the transportation problem, and we'll be doing that also in the upcoming lectures. So a product is to be shipped in the amounts A1, A2 up till AM from M shipping origins and received in the amounts B1, B2 up till Bn at the shipping destinations. So transportation problem, as the name suggests, that we have certain origins and you want from the origin to the transportation of the finished products to their destinations. So the cost of shipping a unit from the ith origin to the jth destination is known for all the combinations of the origins and their destinations. So the problem is to determine the amount to be shipped from each origin to the each destination such that the total transportation cost is minimum. So again, we have a minimum problem, linear programming problem. So certain guidelines that you have to remember while formulating a model. First of all, understand the problem thoroughly, describe the objective, describe each constraint, the decision variables, the most important, what you have to find out. Whether you want to find out the number of bowls and mugs, as I gave you that particular example, so that you can maximize the profits. So you know the cost, you know everything regarding the bowls and mugs, but what should be the number that will give you the maximum profit? So that comes under the category of decision variables. Write the objective in terms of the decision variables. Write the constraints in terms of the decision variables, and like this you will formulate your linear programming problem. So the important one to notice is the decision variables, objective function, and constraint. So let's hear it one by one. What is it? Decision variables are the mathematical symbols representing the levels of activity of an operation. So they are always represented by the x1, x2 up till xn, or if it's a 2 or a 3 variable, you can take x, y, small z, like this. So these are the decision variables. Objective function. Objective function is either it could be the maximum, maximizing your profit, or it would be minimum, minimize your cost. It could be any cost, production cost, shipping cost, transportation cost. So objective function is always and always a real linear relationship. So that means it's of degree 1. The most frequent objective, as I told you, is to maximize the profit. The most frequent objective also is to minimize the cost. So it could be either of these. Constraint, again, it has to be linear relationship with the restriction on the decision variables. So this is how we can formulate our LPP, the linear programming problem. So we have to find out the decision variables. These are called the decision variables. Z is the objective function. It has to be linear. So either we have to maximize our Z or we have to minimize our Z. So it depends upon the question, whether it's maximize profit or minimizing of the cost. So the Z is equal to C1x1 plus C2x2 plus C3x3 up till Cnxn is our objective function, and it is denoted by the equation 1. Subject to the following constraints. So all of these are the constraints, and where Aij, Bi, and Cj are the given constraints. This one is very important, the third equation. These are the second equation, as you can see. This represents the non-negativity constraints. So all the xj's, as we are talking about the decision variables, we are talking about the number of the products or maybe any thing in our question. The decision variables can't be negative. They have to be greater than or equal to 0. So that comes under the category of non-negativity constraint. So there are two types of constraints. It is less than equal to, greater than equal to. The sign could be any. It could be either this, equal to, or greater than equal to. It depends upon question to question. So in the matrix format, if I wish to write my general form of the LPP, so it would be Z is equal to C transpose X, where as we know, C would be our the coefficients, right? C1, C2, and so on, and the coefficients matrix, and X would be our X1, X2 up till Xn, the decision variables. AX, as we know, A would be the matrix where we'll be talking about the coefficients of the xi's in the constraints, with the X less than equal to the bi's. So again, the B would be B1, B2 up till Bm. So here we'll be having an n cross m cross n. This is also n cross 1. So you will be getting an m cross 1 matrix. So this is the first objective function. As you can see, this is our constraints. So this is our objective function. These are our constraints, the inequalities that we have, and this is the non-negativity constraints. So let's talk about one example. So here you can see it's a table given the resource requirements of the product. I am having two products as I am the manufacturer. So the only two products I'm talking about is the bowls and the mugs. For each unit of bowl, I am having the labor, the number of hours of the labor is 1, whereas for the mug it is 2 hours per unit. The clay that means the raw material that I have for bowl is 4 pounds per unit, and whereas for the mugs it is 3 pounds per unit. Revenue means the profit that we are talking about per unit in dollars is given as $40 per unit and $50 per unit. There are 40 hours of labor. So this is the availability of the number of hours of the labor. So I cannot cross 40 hours. So that's important. So 40 is the only limit that we have. 120 pounds of clay, that means the raw material available to me is only 120 pounds. Again, I cannot exceed that. So that's available for each day. So now what would be the decision variables? The decision variables would be the number of bowls that I want to produce, the number of mugs I want to produce. Now what would be my objective function? My objective function would be, because we are talking about revenue here, so my objective function would be maximizing the profit. So that I'm writing it as maximize Z. Now the decision variables I have taken as X1 and X2. Now when we are talking about the profit, the revenue that is given for 1 unit of bowl is 40. So for X1 units, it would be 40 X1. Then for mugs, it is $50 per unit. So for X2, number of mugs, it would be 50 into X2. So this becomes my objective function. Now, what about the constraints? As we know, the constraints would be given by the number of hours that is available for the labor, and the raw material available to us, the maximum is 120 pounds. So let's move ahead and let's see. So the availability is 40 hours and 120 pounds of clay. And as I told you that we have to maximize our Z, 40x1 plus 50x2, where Z is the profit per day we are talking about. Now, what would be the constraint? The constraints would be, as we could see here, for 1 unit of bowl, I have only 1 hour of labor. So the total number of hours that is available to me is 40. I cannot exceed that. So it is less than equals to 40 that I have. On the left hand side, So for 1 unit, I have 1 hour of labor. So for x1 units, it would be 1 into x1 plus for 1 unit of mug, I have 2 hours of labor. So for x2, it would be 2 multiplied by x2. So this would become the constraint for the labor. Now for the clay, on the similar basis, the availability is only 120. I can't exceed that. So for the clay, the number of bowls that I have is x2. So it would be 4 pounds multiplied by x1, sorry. Then mugs is x2, so it would be 3 pounds multiplied by x2. So this is the constraints that we have. So you can see here, this is our objective function. Maximize z is equal to 40x1 plus 50x2. The constraints are this. The non-negativity constraints, very important. X size must be greater than equal to 0 because these are the number of products. They can't be less than 0. So we have, this is our linear programming problem. So as you notice, the first one that we have, the example, this is the same where we are talking about the raw materials and the profit, the labor hours we are talking about. So we can formulate this into a linear programming model with the constraints and the non-negativity constraints.